My name is Fabian Etzold. I'm responsible for the data science team within the Central Research and Development at SCHOTT. Simon is a colleague of mine, and he will give the actual inspiring lecture, as it was called in the agenda. I have the honor to say a few words about SCHOTT before that, and I promise to keep that short so that we can focus on the interesting AI part. Okay, so SCHOTT is a specialty glass manufacturer, and as such has very large product portfolio in multiple markets, and I chose to focus just on two applications to give you an idea of what we're doing. First one is something that I'm very sure of that you all know and have actually also used. Every time you go in your kitchen, you probably have seen the ceramic cooktops, so the Ceran-Kochfelder in German, which is a special glass ceramics, heat shock resistant. It's mechanically stable and highly functionalized for scratch resistance and for easy cleaning. So this is the first product that you probably know from SCHOTT. And the second one is one I chose because I think it's quite cool personally. It's from the consumer electronic section. And you probably noticed that mobile devices, foldable mobile devices somehow experienced a rebirth a little bit. However, without this non-continuous display. Nowadays you can open them and you have a continuous display. And you can imagine that you also need somehow a glass window on top of that. So if you look now out of the window, and you imagine that you fold such a glass window, that's difficult to get your head around, right? So obviously, if you push the process to its limit and make these glass sheets thinner than the human hair, it's possible to fold it because you have a very small radius of curvature then, and it agrees with these mobile devices. So I think that's quite a cool application. It's a high-tech application. And we do have a couple of more of them, but for time reason, I will keep it at this and just show you one more slide with a few numbers to give you an idea of the size of the company. So in fiscal year 21-22, SCHOTT had a global sales of roughly 3 billion euros with an earning before interest and taxes of 422 million euros. And the last number I want to mention here is that we have worldwide 17,200 employees. Headquarters is in Mainz. Of course, your colleagues from Jena know also our production site, which is, I don't know exactly in which direction, but close by. Someone may point this direction, thank you. And maybe one more thing I would like to mention is very recent news. Just last week, SCHOTT was awarded the Deutsche Nachhaltigkeit Award. I don't know what that is in English, Sustainability Award. So this is something worth mentioning for our strategy, how to be climate neutral in 2030. This much to SCHOTT, then one more slide to data science at SCHOTT within the Central Research and Development. We are a small team, 7 people in total, so we're not doing actual AI research, but our task is to evaluate and to check which methods, algorithms, and so on are on the market and which we can actually benefit from in production at SCHOTT. So as such, we're connected to the whole value chain of glass development, starting with material development, melting, then forming this molten glass somehow into a product in the hot forming, and then afterwards the finishing with regards to laser processing or functionalizing with coatings. So we're connected to all of that, and our usual projects are in the direction of something's not working in production. Could you please take a look in the data and see if you can find a reason for that? So it's root cause analysis. Second thing is user assistance systems. So how can we support our operators in production to make their lives easier, and also of course to optimize the processes. Simon will tell a little bit about user assistance systems. And then I will skip the next two parts, but one important thing is the data science training, because for a big glass manufacturing company, data science might not be the first thing to think of, but data literacy is very important also in such a company, and therefore we provide data science training, and to stress the idea of how important it is to deal with data, to care for data quality, so that we can actually do something with the data that is collected. And with that, I will hand over to Simon. Thank you very much.
Yeah, so without further ado, let's jump right to the core. So I've brought you a schematic of a glass manufacturing line or glass production line. I have no background in glass manufacturing myself, so I'll skip the lower details. So basically, what you see here is you put your raw materials in on the left-hand side and glass comes out on the right-hand side, as simple as that, I guess. I've been told that some people say that it's a large chemical reactor, so many things happen inside, and since we are, as mentioned, a manufacturer of special glass, we have pretty tight margins when it comes to quality, so we have to control this process very well. How do you control such a process? Of course, you have sensors, and you don't have just one sensor at the beginning. You have a large multitude of different sensors here. For example, you get temperature, but you also can control for the flow, speed of glass, etc. And what makes it especially difficult is when you put your laser pointer to work, when you put your raw materials in on the left-hand side until you get the glass out on the right-hand side, depending on the sort of glass, you have a lead time of between 24 to 48 hours. So if something goes wrong on the left-hand side and the glass melt, you notice it about like 24 hours later, and everything that happens in between goes to waste. So we basically want to reduce that. And this is where the topic of anomaly detection in the production line powered by AI comes to use. So what we are dealing with is sensor data, and it's time series data. As I said, we monitor this process over time. We have multivariate data coming in from different data arrays. So what I'm showing here is, I think, roughly like 50 to 60 sensors over a period of 3 months. So it's pretty hard to distinguish by eye what you're seeing here. But what you can clearly see is that something isn't right about here. Something is happening here. There's a hiccup in the production, and we want to account for that. I'm moving a lot. Is the volume actually okay? Because I'm not standing in front of you. Okay, guys in the back nodding. So how do we account now for anomalies that are happening? As I said, we have different sensor data, for example, voltage, temperature, and also, there's some motors in there. We also control for them. And because it's hard to grasp for the human eye, especially on a large time scale, we apply machine learning here. So it's, from a machine learning standpoint, a semi-supervised learning problem. So we don't have labels telling, okay, at this point in time, there's an anomaly happening, and at this point in time, there's not an anomaly happening. We have to find that out by manually tagging the data for ourselves, and this is pretty labor-consuming, thus costly. For example, we could, as I said, eyeball this problem here and say, okay, there's something happening here, and then we back-check with the guys at the production line, see if they noted something in their logbook, saying, okay, there was something happening here, and we note it down in our data. So we manually define for the supervised or semi-supervised learning problem, there is the point in time you want to detect with your algorithm. So yeah, basic stuff from a machine learning point of view, so to say. Then we split that in the usual way, training test data. And what we want our model to recognize is a state without anomalies. So this is how it should be in production, and this is how we not want it to be. So we train our model to perfectly, or maybe to overfitly, an actual word, I don't know. We overfit our model to this state to perfectly distinguish the animal state here. And in the end, we want our model to tag this autonomously, saying, okay, there's something happening here, there's something happening there in your data in production. And how do we do that from an algorithmic point of view? Just a high-level workflow here, so sensor data coming in, multiple sensors here. And then we apply a machine learning model as a first step to boil down the complexity of the process. So we have a multitude of sensors showing 50 to 60 here, but let's assume you have 1,000 sensors all over the production line. We then boil that down to a single time series. So we're still in the time domain here, and as you can see, if you move through time, this model then tells you how normal or vice versa, anormal your system is running. So the graph here goes up, this is showing the anomaly score, something is clearly wrong. But as I mentioned, this is a slow process. Imagine you are controlling this production line and you're looking at a display for like 8 hours per shift. It's happening really slow, you can't just pay attention all the time. So you need your model to raise alarms, to raise flags based on this data and warning you if you have to take a closer look. So this is where the second step comes in with rolling window statistics. We want to raise those flags or set those markers when the human has to take a look what is going on inside the system. So we have a workflow with 2 steps basically. There are 3 types of anomalies we are accounting for. There are many more, but those are the most common types in our production lines. So point anomalies, level shift anomalies, and also those slow drifting anomalies when sensors degrade, for example. there's a last step in the value chain, so to say. We also apply explainable AI. You heard a lot about explainable AI today, so I won't go into the details as well. But imagine you have this system with the anomaly score, and the flag is raised telling the operator, hey, take a closer look here. Where should he or she take a closer look now? In the beginning, in the end, as I said, you have a multitude of sensors here, and what explainable AI does for you, or should do here, is, okay, you have an anomaly, please take a look at the beginning of your float path, for example. Because talking about root cause analysis, you want to know where the root of your problem lies. That's what XAI is for. Also brought in an example here, so clearly something's going on. You can see that by eye. So imagine we have an incident here in the production, and this is actually something that really happened. We looked in the production logbook, and there the operators noted that at roughly 7:15 a.m. something happened. Won't go into details here. And then retrospectively, we applied one of the models, and yeah, luckily it was able to flag this point in time here. This is around 6 a.m. in the morning, so if this had been in production by then, this would have given the operators like 35 more minutes to get to the root of the problem and to take countermeasures, so to say. So there is an added business value here, speaking in that term. And just to round it up, I quickly want to show you what algorithms and also tech stack stuff we are using. So for the algorithms, the tools we're using, it's more like, yeah, call it classical machine learning with linear regression, PCA. We are trying all that out and see what works best on our problem. So as it was mentioned before, not every algorithm is suited for your particular problem. We also explored artificial neural networks like autoencoders or transformer networks with self-attention. Also works pretty good on time series. Also tree-based methods, classical filtering models like the Kalman filter, and we also want to apply hybrid modeling in the future. We also heard something about that previously when it comes to combining machine learning with simulation data from the production lines, for example. Quick glimpse on the tech stack. We also use Python here, so the classical machine learning tech stack, scikit-learn, pandas, sharp values, PyTorch. For tuning, we use ClearML and Optuna, and when it comes down to rapid prototyping with UI and deploying, we use Streamlit and Docker containers for that. So yeah, a lot of nice icons. So to sum it up now for good, I just want to present you with what we found out during experimentations and what were the pain points in the process. So first, I think we also heard that before, user acceptance is key. You cannot just waltz into production and say, hey guys, we have a fancy tool, you are now forced to use it, goodbye. That's not how it works. They have to see a value, they have to want to use it because you need their feedback to make it work in the end. Stable software and interfaces were also an issue because if your fancy new machine learning model comes out of academia, just someone drops a paper, drops some code on GitHub, and it runs on his or her machine, yeah, nice, but in a rapid prototyping process, you cannot really use that. You have to make it run on your machine. You have to make it run in a container, and you have to be able to use it quickly to see if it works for you and if you want to use it or throw it away in the end. Data quality, always an issue. You have to do a lot of pre-processing, sensors fail. You have to impute for missing values. You have to, a colleague of mine called it massaging the data. It's like 70 to 80% of a data scientist's daily work is accounting for data quality. Process complexity is also an issue. I haven't got a background in glass manufacturing myself, so I have to talk a lot to the guys who make it work, to the physics guys and to the machine and the engineering guys and girls, and yeah, that's pretty hard to understand. It's a complex process. And also, when it comes down to accessing data in a production environment, access rights are also an issue because I may not have all the access rights to data. Something is confidential, but I would need that data. And what we've learned throughout the process, I also mentioned that this Occam's razor still holds true. Sometimes the most obvious solution for your problem might be the best. So linear regression might work better than your fancy transformer model because it's easier to tune and maybe it yields a higher precision for your problem. As unsexy as that might sound when you buzz wording stuff. Sensor corrosion is also a problem because you're dealing with high temperatures and everything you stick inside to measure something, it degrades over time. That's just how it is, and you have to account for that. This, for example, introduces the drift anomaly. Preprocessing, as I said, a huge part of the daily work, and also communication as, I don't know the English word, but as abgedroschen, as beaten off as it sounds, you have to communicate early on with the process expert and also with the people in IT if you want to bring it into production, because that's where the model leaves your domain and your control, basically. I guess I was talking pretty fast in the end. But that's the last slide. Thank you for your attention, and